All right, so 4.3 is connecting. Okay, we're focusing. Like this is it. Next time I gotta stop, you're moving, okay? Okay. So connecting f prime and double prime with graphs of f. So we're looking at the first derivative and the second derivative. We're connecting it with the graph. Okay. So as you can see in the figure below, a function may have local extrema at some critical points while failing to have local extrema at the others. What this means is we have several critical points here, right? We have several points where our first derivative is equal to 0 or is undefined. But not all of them are going to be actually max or mins. All right, so we have, what? So we're looking at the derivative. All the things I highlight are the derivative, the first derivative. Remember, our critical points occur wherever our derivative is 0 or undefined. Those are where our max and mins occur. But not every critical point has a max or min. So notice we have a slope of 0 at this point, right? So this is critical point 1. Slope of 0, but we don't actually have extrema here. We're not coming up to a max and back down. We're not going down to a min and back up. We just kind of like flatten out and then we go back up. So there's technically no extrema right here.
Isn't that local though?
It's not a max, because to be a maximum, you have to be bigger than both numbers that are next to you, both y values. You have to actually have a hump. Huh?
What's the local one?
This is a local max right here. This is a local min, because notice this point is smaller than both on both sides.
So that, okay.
Hold on. Okay, so first question.
Is the reason that it's undefined there is because it's a cusp? Is that what it is? Or
Yeah,
is it like, okay.
That's why. Okay, so I'm going to name this like this is critical point 1. And remember, CP means critical point. So critical points, places where you have max or mins, occur where your first derivative is 0 or where it is undefined. Okay, so we have several critical points here, but not all of them have maxes or mins with them. This first critical point, number 1, it doesn't actually have extrema. So at this point right here, I have a slope of 0. It's flat. Because the graph comes up, it flattens out, but then it comes back up. So this point right here is smaller than the side that's after it, but it's bigger than what's on the left of it. So it's actually not an extrema.
But it is a critical.
It is a critical point, but it didn't give me an extrema. Because I'm coming up and I'm coming up, right? The derivative would be positive on both sides. That's not actual extrema. Okay, let's look at critical point number 2. Right? This is a local max because it's bigger than the numbers on the right. It's bigger than numbers on the right? The y value right here is the biggest in the local vicinity. So it's a local maximum. Right? Because we're going from increasing to decreasing. Versus over here, we were just increasing on both sides. So whenever you go from increasing to decreasing, you have a max. We go to the next example. So I named this critical point 2. So at critical point number 3, we have a local min. Right? Because I'm going from decreasing to increasing. Whenever you're going from down to coming up, you go through a min. Okay. And notice that this is where our derivative is equal to 0. So far, we've dealt with derivatives equal to 0. So we have a shot that it actually won't be a max or min because it just levels out and then goes back up. We could have a maximum, or we could have minimum. So those are when derivatives equal to 0. Now we'll go through the times where it could be undefined, where our derivative could be undefined, yeah?
I forget. It's like not on topic, but is that if our critical points are undefined is 0, how do we know how many of them?
It's whenever your first derivative is 0 or undefined, those are going to be your critical points. And then once you find those like x values where the critical points occur, you plug back into your original function, and then you look at like, oh, which is the highest? That's my max. Which is the lowest? That's my min. Yeah. So we draw the number line. We see, right? The number line is like what I'm trying to draw, like right here. This is what I was drawing. All right. We draw a number line here at this point, C3. I see the derivative is down to left of it. The derivative is up going to the right because right derivative means slope. The slope is negative coming down. So that means this is the graph of f prime. So if I'm talking about the graph of f, right, the actual function, that means it's going down and then going up, and then that's how I know it's a min right there. So you draw the number line, and then that also helps you determine which ones to plug in. Yeah. Okay, let's look at this one. Oh, the function is undefined here, but we see our derivative is coming up. It's increasing, and then our derivative goes down. So that's how we know it's a max. So this is undefined here because it's cusp. Cusp is more, let's see. Cusp is more approaching infinity on both sides. So I'd have to say it's a corner, because technically the slope right there would be, I'm talking about the tangent at that point would be a real number. So it's more of a corner. I mean, you could like fight me on it, but I don't see the right side going to like positive or negative infinity. So on the as I come from the right side, okay, I can see how this is approaching infinity. Ambiguous. Yeah, whatever. Normally when I make a cusp, it's going to be very clear, or a corner is more, like I normally make it more clear. Okay, or another example, we could have no extrema. So notice the derivative is negative on the right side, and it's negative on the right. No change means I'm not actually changing direction. I'm not going to actually have a max or min. Okay, and then of course, whenever we're talking about max and mins, we have to include our endpoints. Okay, so nice little review. So first, theorem 4, first derivative test for local extrema. This is what we've been doing. This is a review of 4.2. So first derivative test for local extrema. First derivative. We find the first derivative. Wherever that's equal to 0, those are our critical points. And then looking at our derivative tells us if we're going to have a max or a min. Okay, so for example, at a critical point C, if it changes from positive to negative, then we have a local max. So, right, f prime is greater than 0, that means positive. F prime is less than 0, that means negative. So if we're changing from a positive slope going up to a negative slope going down, that means we had a little Humpty Dumpty, we go up to a max and then come back down. So at our critical point, the slope is 0 because the tangent line would be flat right here. So the example of having a max where our slope is undefined. So this one is this is definitely a cusp, because right, if you approach from the left side, your slope goes like vertical. Approach from the right side, the slope goes vertical. So the slope is greater than 0 is positive. The slope is less than 0 negative. Whenever you're going from positive to negative, that's when you have a maximum. Did we already cover this? Yes. Yes, we have. Confidence. Yes, we got it. You know what to do. All right. If our derivative, right, if our slope goes from negative to positive, think about what that means. Goes from negative going down slope. Positive means going up. So going from down to up means we have a minimum. So if I'm going from negative to positive, means I'm going from going down to up, and I'll have a minimum. From negative to positive, so at this point right here, this is a corner because I have a specific slope on the left. I have a specific number slope on the right. So if I would draw a graph of my slopes, this is why it's a corner, because I actually have numbers. Let's see, certain slope till here, and then I have a positive slope. This is what the graph of f prime of x would look like. This is why the slope is undefined at C. Actually, this should be at point C. Because as I approach from the left side, I have a different slope than as I approach from the right side. Okay, anyway, so you're changing from going down, a negative slope, to up, positive slope, positive derivative, which means it's a min. And then here's our very special case. So we started getting into this last time. Remember when we had some holes, right? We dealt with some holes and we're like, well, okay, I wasn't sure if my graph would look something like this. I wasn't sure if my graph was going to come up this way or if it was going to be coming up like that. All right, so it is a point, if our graph looks something like this, it is a critical point right here at C, but it's not a max or a min, right? Okay, I think that was a little confusing. Let me erase that. Okay, so if the sign doesn't change, you have no local extrema. So if you do not change the sign of your slope, it goes from being positive to positive. Wait, that's not giving me a min or a max, right? So positive to positive. Or if it's a negative to negative. It's not actually like swooping and coming back up or like coming back down. So on the left side, I see I have a positive slope. So wait, I'm not actually coming back down to be a max. So no extrema. And on the right side, I have a negative slope. I have a negative slope. Slope here is just the derivative. So no change means no max or min. Okay. How do you feel about this so far? One page done.
Good.
Yeah, our goal is to get through.
All of it.
No. Bottom page 15. That's our goal. Get through 15. But like right now, this is just. I mean, there's a whole nother page of just.
Wait, Miss O'Brien, so tomorrow, like, the basketball girls are missing half
I'm gonna
of this
screencast.
period.
Yeah, we should be able to finish 4.3 before you leave.
Great.
Hopefully. I'll screencast. I mean, as long as I'm here, if people are gone, I screencast. I mean, I was gone Friday, so I was sick, so I didn't screencast the lesson for my kids. Then they were gone. Wow.
It was a joke.
Woo, okay.
It was a joke. It was a joke.
Woo.
I'm a nice
All right,
person,
ready?
stop.
And focus. Okay. Oh my god. Oh, wait a second. Focus. Ty, what are you doing? Are you talking?
He goes, ask her if she was there on Saturday. She was taking score.
Yeah, it was a scoreboard. You get new shoes?
Yeah, they're really nice.
Well, I wasn't asking you guys. I was asking Ty. You did? Yeah. Angel and I thought they were really cool.
I
Yes.
really appreciate that.
She's the Alvin's daughter. She keeps score.
That's one of the best compliments I've ever received.
Okay.
That was so sweet.
No, it's special to us.
Okay. They're really cool. Angel and I want to buy them. All right. And here we go. So. Think about your grade. I want you to have 100. Here we go. I mean, you know you don't have to take this class, right? You don't have to be
I
here.
need to take it.
Okay, then think about that motivation.
Drop math second semester. Not that I'm thinking.
Talk to your college counselor.
My dad said.
Okay. Left. So, all right, guys. So imagine. Oh my God. And okay, who am I moving? Noah comes in the front, right over here. Let's see. Do I need to separate? Did I separate you? Okay. No, just move up. All right. That way, if you want to talk to Gabe, you have to turn around. It's easier to see you. Make mistakes.
You think it's gonna stop them?
No. Just move for me. Just move for me.
This is like last year.
Okay. So.
Come on.
So what we've been talking about so far is having max and mins, but now we have to talk about the endpoints, because remember our endpoints could be a local max or min. So how do we determine if we have a max or min at our endpoint? That's the idea right now. So let's say I'm starting at A. All right, something like this, and maybe my graph goes that way. If our slope, so what I'm doing is I'm describing, if f prime is less than 0 for x is greater than A, if the slope, the derivative, is negative for all of our x values greater than our left endpoint, guess what's happening? So if our slope, right, because this is the derivative, if our slope is negative for all the x values greater than A is our endpoint, so if for all these x's over here our slope is negative, guess what A is?
Oh,
Our max. It's our maximum. Just think about it. If our slope is negative, it's going down. If our slope's negative, it's going down. And if it's negative for all the values to the right of A, that means A has to be the max because everything's going down from
Oh,
there.
we're looking for A.
I'm just looking for what's happening at my
But we don't
endpoint.
know where X is. What if it's like one of those ones where it goes
So-
like straight?
Well, because we're saying the derivative is less than 0. So as long as our derivative is negative when x, right, when our numbers are bigger than our left endpoint, as long as the slope is negative going down, that means that our endpoint it will be the max. That's all this is saying. I'm trying to take this whole part right here and describe in English what it means, because you know what it means. You just don't know like what it means when it's written this way. But unfortunately, it has to be written this way. So my job as a translator is telling you, oh, look, You know, you understand this, all right? So I have an endpoint A, and I'm going on to forever, and I'm going to draw out my derivative. My derivative is negative. So that means my actual function, so I'm drawing it in blue, is going down. Oh, wait, if it's down, that means that this point over here has to be my maximum. That means I have to have a max right here because all of the rest of my y values are less than it as I go to the right.
Oh.
Yeah, see, you know what it means. You already know this. It's just making sure you understand, like, the language of math. That's what holds people back. You don't know how to translate it. Who wants to give a shot at this? Who can translate this sentence for me? All right. Hannah, you literally had your hand up first.
So it's the opposite of what you just said. So if the derivative is positive between 2 points, so if it's just going up between 2 points, then the local minimum is going to be the first point.
When you asked for it, no, I was going to, but now you asked no.
I asked for it as a joke.
No.
If
you say ask for it as a joke, it's like a minus.
Okay. So, drawing in 2 different colors so you can see. So, what this means is if f prime of x is greater, if f prime is greater than 0, if the slope's positive, right? Slope's positive, going up. For x greater than a, for all of our x values that are bigger than our left endpoint, aka we have our left bound a and all the numbers in our bounds, okay? So if the slope is positive for all the values we care about, that means a has to be the smallest, it has to be a minimum.
Wait, I do have a question.
Yes.
So that means that your, like, okay, it says local min.
Yes.
If your slope is positive for everything to the right of it.
It'd be our absolute as well.
Oh.
But the reason I am saying like local min is because we're gonna have like a bunch, and I want you to understand like what's happening at my bound. Yeah. Because imagine that I had something like this, where here's A, and then I have a couple other things down, up. I want you to understand that it is a local min, and then we have to plug in numbers to see if it is our absolute. Yeah. So we'll plug in numbers later. Okay. You understand that part. Cool. So as I said, if the derivative is greater than 0 for all of the x values we care about, right, all the ones to the right of it, that means it's a min. And also, this is showing you the graph right here. So at the right endpoint, if our derivative is less than 0, if we have a negative slope, for all the x values less than b, so b is our right endpoint, so for all the x values to the left of our right endpoint, if the slope is negative, guess what's happening here? It's going to be a minimum. Luckily, I wrote it for you. Okay. So here is b. Notice b is my right end, right? That's where I'm ending. And we said that the slope was negative, means it's going down, which means that this is a minimum. So going down, which means this is a min. So we worked on like the inside portion, the previous page. This is working on like the outside portion. Now we're gonna go through and like have a bunch together and decide what our min and maxes are. All right, last one. If f prime is greater than 0 for x less than b, then f has a local max at b. Okay, break it down. So if we have a positive slope, right, it's going to be going up for all the values before b. All right, so b is our right endpoint. So we're looking at all the values to the left of our right, to the left of our right endpoint. So here's my right endpoint is b. And we said the slope is positive, which means it's going to be going up, right? My actual graph is going to be going up. This means it's going to be a max. Did I say that backwards? I don't think so. Okay, cool. Another page done. 3 more to go. Let's go. So use the first derivative test. Oh, literally what we've just been doing. The first derivative test, determine the local extreme values of the function, support your answers graphically. What that means is the number line that we've been doing. That's graphically. So first, we must say the domain. The domain of this polynomial function, all real numbers, negative infinity to infinity. So the reason we do this is to make sure if there's any holes, that can't actually be a critical point. If there's any holes, we can't include them in our domain. Okay, step one
Let's
done.
say there is a max, but the top is a hole. Then it would.
So we would. So we can't include a place where it's a hole.
Okay, so it just wouldn't be a max or you just would ignore it. Okay.
If there's a specific question on the homework, you can also come and ask me.
Okay.
It's my water bottle. I squeezed her water bottle.
Okay, so I need to, first derivative test, I have to take the first derivative. F prime of x is 3x squared minus 12. Then, to find critical points, you see, right? We want to find the critical points. Critical points are where f prime is equal to 0 or f prime is undefined. So, since this is a polynomial, 3x squared minus 12, you know what that looks like. It's never going to be undefined. It's literally a parabola. So, it's not defined anywhere, so I just have to set it equal to 0. Factor, so I'm going to pull out a 3. I mean, this is a difference of squares. You didn't know, x squared minus 4 factors into x minus 2, x plus 2. And then define the critical points, you just set each of them equal to 0. So x is plus or minus 2. These are my critical points. So I'll pause here for a second, make sure I'm not...
Do we put 3 on the number line?
No.
Just your critical.
Because 3 doesn't give me a solution, right? I could technically divide both sides by 3 and it would be gone.
But if it was x, then it'd be
Right. If this was x, right? Oh, that's a good point. If this was x right here instead, you would have to set equals 0. Told you hear what I said?
Yeah.
What'd I say? No, you have no clue what I'm saying.
No, if you said if there's 3x and you have to set it equal.
If it was x instead of 3, you'd have to set equals 0. That'd be another critical point.
I did hear you.
Okay. All right. Now that we have our critical points, you draw a number line. Draw a number line. So we're going from negative infinity to infinity. The only reason I'm writing this as my bounds is later when we have a bounded domain, I literally have to write my stoppers at the end.
Really?
And then my two critical points, it's the next problem.
Oh,
Negative 2 to 2. Negative 2 and 2 are my critical points. So
Let's plug it in.
now
You gotta keep plugging into your.
so first we have to do the first derivative test. Plug into the first derivative. Okay? Plugging into this right here to find our derivative. If I put in a number less than negative 2, let's say like negative 3. Right, the 3 doesn't matter. Negative minus, okay, that's negative, negative. So this is a negative times a negative, which is positive. So let me just take 2 seconds to make sure we're all clear with what I did. I plugged in negative 3. I don't really need to know the numbers. But what I do know is this is going to be negative times a negative, which turns out to be positive. And then it just switches. Minus, plus. Thank you, multiplicity. Right? Because it switches from plus, minus. Now that we have the derivative, I'm going to go back and I'm going to say, okay, what is happening to our actual function? Notice, different color. One is prime, one is not. This is the real function. What is our graph? What would it look like? Oh, up. Positive goes up. Negative goes down. Positive goes up. So when I'm switching from going up to going down,
max.
I have a max. When I'm switching from going down to going up, I have a min. And since these aren't actually bounds, right? We don't have an endpoint. If this was like a number, like 5, right? If we're ending at 5, this would be a max. If I was ending at negative 3, this would be a min. But because they go to negative infinity, we don't like say.
And your endpoints would be your absolute, and those two in the middle would be your locals.
Depending on the y values. Yeah. Okay, so we see we have a max, we have a min. So if I plug in my values there, so I know that my max is going to occur at negative 2. So if you plug negative 2 back into your original function to find the actual y value of your max. So negative 2 cubed is negative 8, plus 24 is 16, minus 5 is 11. Our min, we said, was going to occur at x value of 2. So we plug in here, we have 8, minus 24 is negative 16, minus 5 is negative 21. Just plugging back into my original function. Okay, so this isn't different than what we did in 4.2. This is a good review of 4.2, and the reason we're doing this so you can understand the concavity test. We're going to take it one step further. Don't worry, that's the next page. We're going to do one more example before we go on to the new stuff.
This makes my heart feel concave on the inside.
Do you know what concave
It means
means?
like there's a hole in it. No, it's like
Going
just
in,
facing
right?
in.
It means like if you have a bowl, it's concave up, bowl facing down, concave down.
That's so mean.
What's
I
wrong?
did it, like, tell you, and then it'll last seconds.
What?
Please go at the same time.
Go bathroom? Sure, there's a bathroom pass. Go ahead. All right, let's do B. I'm screencasting anyway. All right, so B. I want you guys to try the first one. What is my, well, actually, just kidding. They're giving us our domain. Our domain is -5 to 5.
Cool.
Okay, next step, we need to find the first derivative.
Which I don't know.
So let's find the first derivative.
It's
Product rule.
Oh my god.
Product rule, because we have one thing multiplied by another. So now have u equal x squared minus 3. So let's see, the derivative of this would be 2x. V is e to the x. So v prime is e to the x. It's itself. This is also why I gave you that fourth assignment of review. So that way you will be good with this. Because I don't want to have to take and reteach product rule. Like, you should know what it is, how to do it. So f prime of x is going to be 2x times e to the x plus e to the x times x squared minus 3. I'm going to simplify this a little bit because there's a common factor, e to the x, right? So let's pull out e to the x. E to the x times, let's see, 2x plus x squared. I'm going to rewrite this in a different order. X squared plus 2x minus 3.
And that's factorable.
Actually, I'm sorry. I'm not going to be lazy. I'm going to show you exactly what I'm doing. I'm sorry. It's the exact same thing. You don't have to erase. I just want to show you, I pulled out e to the x, and then I'm rearranging it. That way I can fully factor. Okay. I'll scroll up a little bit.
Wait.
So we have our derivative. I need to fully factor it out. Plus 3 minus 1. Was that what you were going to say?
Yeah, but I have a question. But it's after that.
Okay. E to the x, x plus 3,
Wait.
x minus 1. Yes.
How can you make x squared into 2x?
I didn't. So I pulled out e to the x from both these terms, right? That's how I got 2x plus x squared minus 3. Then I just moved the order around, so that way it was in a normal quadratic form. And then I can factor that.
Oh, that was really
That's why I did 2 different lines, just so you could see that. That's why.
Thank you.
Okay, so we have it fully factored. Okay, we have our derivative. We need to find the critical points. The critical points are always where our first derivative is equal to 0, or it is undefined. Okay, so where it's 0 or where it's undefined. Is this ever going to be undefined? Right, is e to the x is continuous for all real numbers. Each one of these factors is continuous, so it's not ever going to be undefined. But what I can do is set my derivative equal to 0, okay? Or f prime of x is undefined, is where our critical points. I'm just writing this, so that way, like, it's beat into your brain. Okay, set equal to 0. 0 equals e to the x plus 3 times x minus 1, and we set each of these factors equal to 0. Question, where is e to the x equal to 0?
Never.
Exactly, it's never equal to 0. So it's always going to be positive. That doesn't help us. Where are my critical points?
1 and -3.
Yeah, -3 and 1. These are my critical points. Okay, think about what the next thing we need to do. Number line. Go ahead, draw the number line. I won't be angry if you work ahead and you try this yourself. So I have endpoints here, -5 and 5, because I'm not going for all real numbers, so I have distinct endpoints. And then -3 and 1 are both in my domain, right, between -5 and 5, so I include them both. Then I need to decide what is happening with my derivative. Let's see, let's pick 0. That'd be the easiest one to do. If I put in 0, I mean this first e to the x will always give us a positive number. Let's see, so it's going to be a positive, then negative, so that'll be negative here, and then multiplicity, it just switches back and forth. Cool. Okay. Then I need to understand, okay, if that's what's happening with my derivative, let's talk about what's happening with my real just function, right? No, it's not f prime, it's our original function. If we have a positive slope, it's going up, negative slope goes down, positive slope goes up. Yes?
Can I explain it?
Sure, go ahead.
So, you know for certain that the minimum is going to be x equals 1, but you don't know because you have two local maximums. So you have to like plug both of them in to see which one's more maximum.
Okay, where's my other max?
At 5.
And where's my other min?
Oh, I totally forgot about that one.
Ah, tricky trick, right? Because we have endpoints, we also are going to have max and mins there. So now we have to, we can figure out what they will be. It just said local extrema, so as long as we find our max and mins, we don't need to necessarily say which one's absolute.
Oh.
Because the directions just say local extreme. Okay, so as Hannah said, our maximums are going to be at f of negative 3 and f of 5, and our mins are going to occur at f of negative 5 and f of 1. So let's plug in negative 3. Let's see, max is at negative 3 and 5. Okay, so if I plug in negative 3 squared is 9, minus 3 is 6 times e to the negative 3, which is just 6 over e to the third power. So I'm plugging this into my original function to figure out what the y value would be.
Should we keep it like that, or do you want to?
6 over e to the third is fine because remember, simplified means no negative exponents.
But like you don't want us to plug it into the calculator?
You don't necessarily need it because you can compare them and know which one's bigger. If I plug in 5 squared is 25, minus 3 is 22 times e to the fifth. So which is bigger, 6 divided by e cubed or 22 times e to the fifth? Right, so this one would be our absolute if we were asking. But, we're not, but now you know. Okay. Let's plug in negative 5. So negative 5 squared is 25, minus 3 is 22, but it is e to the negative 5, so 22 over e to the fifth. All I'm doing is...
Like a math
thank you. Negative 5 times negative 5? 25. Minus 3? 22. Times e to the negative fifth? Well, it's just 22 over e to the fifth.
What?
Okay, let's try the next one. F of 1. Plug in 1. 1 squared is? 1. Minus 3. 1 minus 3? Negative 2. E to the first. Negative 2e. Negative 2e. Negative 2e. Okay.
I would have never even thought to do it.
So, which is smaller? Well, that's an issue. That's why we have the
Oh my God,
fourth
22 over
assignment
e to
is
the
the
fifth.
review of last semester.
So,
22 over e to the fifth is smaller.
You should probably review and learn. Yeah. All right, Hannah, what'd you say?
22 over e to the fifth is smaller.
Yeah, this is definitely the smallest. So this is what our absolute min is. So you didn't really need the calculator to figure out. 22 divided by e to the fifth is a really, really big number. Right, which is bigger, e or 1 over e? E, right? That's why, sorry. It's a negative. I forgot that was negative. Got him. It's a negative, so it's actually smaller. Just kidding.
But if it was positive, then the one.
If it was positive, then the other one would be. All right.
I see another dad.
It is what it is. You go to the bathroom, you missed. You have to get it online. All right, concavity. So, concavity. I upload the field notes. We have a screencast. You go to the bathroom, you miss class. I'm keep going. I can't wait. Concavity. So, the graph of a differentiable function, y equals f of x, is concave up, right? Concave up goes up. On an open interval, if the derivative is increasing, concave down if it's decreasing. All right, so this left one is concave up. This right one is concave down. Okay, so your concave up if your derivative, your first derivative, is always increasing, you'll be concave up. So there's two ways you can be concave up. All right, there's two ways. Let me change this color to be red. That way you can tell the difference. All right, so there's two ways you can be concave up. So you can be like this one. So when you're going down, your derivative is always increasing because it goes from a big negative number to a smaller negative number. Yeah, so the derivative is increasing. It's getting bigger because you're going from a big negative to a small negative, right? You're increasing. That's why it's concave up, because your derivative is getting bigger. When you go from a big negative to a smaller negative, you're getting bigger.
But the line's going down.
I know.
Oh man. So is it flip? Wait, so
This is why I'm going through it like this.
so
Because let's say the derivative is like -4 here and -1 there. -4 is getting bigger and it's going -1. It's getting more positive.
so you test it on different points. Is that right?
I mean, sure, that's going to take a long
Wait,
time.
as long as it's like facing this way and not like that, then it's.
So if you are
Oh, I kind of get
like
it.
curving up, like
Yeah.
curving up is concave up.
It's
Like
like
if the
You're
spoon
curving
is,
up.
the spoon is
Curving up.
scooping,
Yeah.
you're getting ice cream. That's
Yep.
good.
and if it's
So
down,
it's
you're
going
just
up. And if the spoon is facing down,
it's just like
the ice cream is just gonna slip off.
on the floor.
It's down. Not good.
This is
Wait, that's how I'm gonna think about it.
Yeah, fine.
sure. Okay, so concave up, your derivative is increasing. That's good. It's literally a spoon increasing. It's like, well, this one up here is concave up. It's like a container facing up, concave up, versus concave down is a container facing
Think of a
down.
spoon with the ice cream, trust me.
So if you're concave down, what would this look like?
Just like that.
Right, something like this, where the derivative is getting smaller. So over here, let's say this is a derivative of like 5, and then 1. It's getting smaller, decreasing. Versus this one, this could be a derivative of like 2 versus a derivative of 10. It's getting bigger, right? 2 to 10 is getting bigger. Yeah. Okay, let's talk about the other way, concave down. Something like this.
Yeah.
Because you're going from,
Slip right off.
yeah, because think about the derivative, what the slope, what's happening with my slope. This is a small slope, let's say like -2. But then down here, this is like a -5 slope. Going from a -2 to a -5 is decreasing. You're getting smaller slope. This is a maybe like 5 to 2. 5 to 2 is getting a smaller slope. You're curving off.
So it's like left to right. You're looking.
You're always looking left to right. That's why these little arrows right here are showing you left to right. That's what I meant to say. Okay, so that's concavity. Now we're going to talk about the concavity test. Okay, so we had a first derivative test, which tells us the local max and mins. All right, it tells us if we're increasing, decreasing. Well, the concavity test uses the second derivative. Oh my God, second derivative.
Second derivative, we know how to do that.
You do. So the graph of a twice differentiable function is concave up if the second derivative is greater than 0. It's concave up, right? Scooping up. If the second derivative is negative, it'll be concave down.
So the first derivative doesn't matter for this one?
So you've got to use
I mean,
the first to get to the
Well, I
second.
get that.
Yeah.
That's not the answer.
Whoa.
So let's use the concavity test. So we just have to take Gabe. Woo. Okay. Yeah. Well, you only have like 4 minutes. Yeah. Okay. All right. Ready? First derivative.
You saw that one.
Shh, come on. Tall.
Sorry,
man.
sorry.
First derivative, -4x cubed plus 12x squared minus 4. But then, gotta go one step further. The double, the second derivative. -12x squared.
Plus 24x.
Yep. So, we took a second derivative, and we want to know where it's concave up, where it's concave down. So think about what we just said. The concavity test says if our second derivative is greater than 0, it's concave up. If the second derivative is less than 0, it's concave down. So what about where it's equal to 0?
It's gonna be
Concave
nothing.
even. It's gonna be a line.
It'll be switching from concave up to concave down. Just like where our first derivative was equal to 0, we're switching from going up to going down. Where the second derivative is 0, we're going from,
Concave.
we're going to figure out where our
Up to down.
concavity is,
What do you
switching from
use
concave up to concave down.
In the middle.
Concave number.
What?
Why do we need what do you use concavity for?
Where will be always increasing to always decreasing?
That's how you test.
Because it's weird, because you could have a negative slope but be increasing. Yeah. Okay, so we want to know where is our second derivative equal to 0. So set our second derivative equal to 0. So you have to factor and solve. Well, you have negative x plus 2, and you get the same answer. So I see my two places are at x equals 0 and at x equals 2. These are not critical points. We don't call them critical points because this is not the first derivative. They're technically called points of inflection, which is the next page. Technically, they're called points of inflection because you're switching between your concavities. You're switching from concave up to concave down. Huh? Okay, so they are points of inflection, okay? Critical points are for first derivatives. Points of inflection, second derivative, because we have a second derivative. So, just like how we did the first derivative test, we have to have a number line. Okay, we have a number line. The two places where I'm interested are 0 and 2, because that's where my concavity,
Oh, we are interested in 0 now.
where
Oh.
the places where the second derivative is 0 are where we switch from being concave up to concave down or down to up.
Okay, yeah.
And what does it tell you?
So,
Like, is it like the second derivative, like on the last test thing we did? Is that
we
like
didn't do the
rate?
second derivative yet. This, like, we did the first derivative up here, but this is the second. The first derivative tells us where the max and
slope.
mins.
It tells us the
Yeah,
slope.
this
But
is
what
telling
is
us how the slope is changing. Are we, so not only are you like speeding up or down, but how fast are you speeding up and down? For how long are you speeding up and down? Okay, so if I put in a number less than 0 into my second derivative, I get, let's see, less than 0 would be negative, and then positive, negative. I don't need them. I mean, I could write them, but they're not needed.
Okay.
So what this means is negative means concave down, positive means concave up. These are the symbols for concavity. The U-shapes are symbols for concavity. So what we're trying to find are the intervals for where we're concave up and down. So we're concave up from 0 to 2 and concave down everywhere else. From negative infinity to 0, union 0 to infinity, 0, 2 to infinity. So we, remember, no brackets because we're intervals. Intervals, we don't include the point we're changing. And then this is it. This is the concavity test. You take first derivative, take it again, second derivative. You see, where's our second derivative equal to 0? Because that's where we're switching from concave up to concave down, or down to up. And then you plug in numbers into your second derivative. If it's negative, you know it's going to be concave down. If it's positive, you know it's going to be concave up. And then you just find the intervals. That's it. Write the intervals. Okay, so 14 pages. Let's find what? Okay, so next time we're going to finish 4.3. Please bring your review, so if we have time, we can get to it.
Do you think we'll finish it by 1:40?
I don't know.